LM applications don't just have users and APIs. They have prompts, retrieval pipelines, agents, tools, providers, and logs, each one a possible attack path. In this lesson, we'll learn how to find those risks before attackers do. So far, you've built the operating foundation, how GenAI systems are architected, deployed, observed, evaluated, and improved. Now we shift from reliability to security and governance. Threat modeling comes first because it helps us understand what can go wrong before we choose the right controls. LM threat modeling does not replace traditional application security. It extends it. Users can send open-ended instructions, including attempts to manipulate the model. Retrieved documents and external data can become trusted context, even when they are not trustworthy. Agents may call tools and change real systems. And because outputs are probabilistic, we must plan for unsafe, misleading, or exploitable responses. An LLM application is a hub with many trust boundaries, not just a chat box. User prompts and file uploads may carry malicious instructions, sensitive data, or exploit payloads. Hidden system and developer prompts can be leaked, overridden, or manipulated indirectly through retrieved content. RAG documents, vector entries, logs, feedback, and evaluations can all become attacker-influenced inputs. Every plugin, API, tool, model provider, and orchestration service adds another path for data, identity, and actions. The goal is to identify each crossing, then validate, isolate, monitor, and limit what it can do. Every prompt surface should be treated as a control channel, not just text. System and developer instructions define the rules, policies, routing, and tool behavior the application depends on. But other content can compete for influence. A user may directly ask the model to ignore those rules. Retrieved documents may hide instructions inside content that appears trustworthy. Tool outputs and memory can also flow back into context and affect later responses. The core risk is hierarchy confusion. Untrusted instructions entering the same reasoning space as trusted ones, and quietly changing what the model does. RAG changes the threat model because the model is no longer answering from its parameters alone. It is answering from whatever the retrieval pipeline brings into context. That makes every stage security relevant. Source documents, ingestion, chunking, embeddings, the vector index, retrieval filters, and prompt assembly. A poisoned document can become an instruction. A weak tenant filter can become a data breach. Even embeddings can reveal sensitive relationships without exposing raw files. And if the index is stale, duplicated, or poorly chunked, the answer may be wrong, non-compliant, or manipulated with confidence. Once an LLM connects to tools, the risk shifts from wrong words to wrong actions. Imagine a support agent with CRM and email access. A customer message is retrieved, the model interprets it, then calls an API to update a record or send a response. If permissions are too broad, approval is missing, or parameters are built from untrusted text, an injected instruction can become a real command. Tool outputs can also poison the next step. The control point is not just the model, it is every action boundary. LM security is not limited to your application code. Every outside service becomes part of the trust boundary. A model API may see prompts, retrieve documents, user data, and business context. Logging and tracing tools may quietly preserve secrets, PII, or full outputs. Feedback forms and evaluation sets can become sensitive training assets. Also review SDKs, prompt libraries, open source components, and model artifacts for supply chain risk. The key question is simple. Does data leave your controlled boundary? If yes, verify retention, encryption, access, vendor terms, and deletion controls. OWASP gives teams a shared map for LLM security. The key idea is that risk does not live only inside the model. It appears in prompts, outputs, retrieved knowledge, plugins, tools, and human decisions. Prompt injection can steer behavior. Sensitive data can leak. Poisoned training or vector data can corrupt answers. Excessive agency can let a system take actions it should not. Model denial of service can make an application unusable. Using these categories helps teams move from vague concern to concrete controls, clear ownership, and consistent risk conversations across security, product, and engineering. Prompt injection is easiest to understand when you treat the model as a control room, not just a text box. It happens when untrusted instructions get mixed into the command channel. Direct injection comes from the user. Indirect injection can be hidden in documents, websites, emails, tool results, or retrieved context. The danger grows when model output is treated as executable truth, then sent into SQL, a browser, shell, API, or workflow engine. Defenses separate contexts, validate outputs, use allow lists, escape dangerous characters, filter content, and require human approval before sensitive actions. Not every LLM attack is about taking over the conversation. Some attacks target the classic security triad: integrity, confidentiality, and availability. Poisoning attacks damage integrity by corrupting training data, fine-tuning examples, or retrieved documents, causing biased answers, backdoors, or failures in specific cases. Sensitive disclosure breaks confidentiality when private data leaks through prompts, context, embeddings, logs, traces, or generated responses. Model denial of service attacks availability by forcing expensive work, such as huge prompts, long contexts, recursive tool calls, or high token consumption. A strong LLM security program protects all three, not just prompt injection. Excessive agency means an agent can do more than the task truly requires. The risk is not just one bad tool call. It is the full chain: observe, reason, plan, execute, evaluate, and act again. A harmless step can combine with code execution, database updates, payments, messages, or infrastructure changes to create real-world impact. Threat modeling should test the whole workflow, including permissions, policy checks, validation, and logging. For irreversible, regulated, sensitive, or expensive actions, add human approval before execution, not after damage is already done. Effective LLM threat modeling starts by making the system concrete. Map users, prompts, the application, retrieval, tools, data stores, model providers, and external services. Then trace what moves between them: sensitive data, instructions, embeddings, logs, and outputs. The most important step is marking trust boundaries, because that is where assumptions break. Convert each boundary and data movement into realistic attack scenarios. Finally, rate each scenario by likelihood, impact, exposure, and existing control strength. That ranking tells you which safeguards need owners, deadlines, and validation. Without that discipline, threat modeling becomes brainstorming instead of engineering. Threat modeling becomes useful when high-priority risks turn into owned, testable security requirements. For each threat, define what prevents it, what detects it, and what happens when it occurs. Preventive controls might include least privilege, input filtering, retrieval authorization, and tool allow lists. Detective controls add monitoring, anomaly detection, audit logs, and cost alerts. Responsive controls cover playbooks, key rotation, rollback, failover, and session isolation. Assign an owner, define a validation test, track status, and make these checks part of CI/CD and release readiness. Threat modeling turns LLM security from guesswork into engineering practice. We mapped the expanded attack surface, used OWASP risks as a shared language, and emphasized controls for agentic systems: permissions, approvals, tool use, and audit trails. Next, we'll focus on prompt injection, data leakage, guardrails, identity, authorization, governance, and compliance. Secure by design starts with understanding failure.